In many molecules, the molecular orbitals are combinations of more than two atomic orbitals. Especially, the atomic orbitals of a single atom are usually combined. Let's consider the methane molecule, which has a carbon atom at the center and 4 hydrogen atoms bonded to it. The valence shell of carbon atom is 2s2, 2p2. We know that the 2s orbital and the 2p orbitals have different shapes and energies. If each bond is formed by the overlap of one atomic orbital in carbon and one atomic orbital in hydrogen, there should be a bond by the overlap of the carbon 2s orbital and hydrogen 1s orbital, and 3 identical bonds by the overlaps of the carbon 2p orbitals and the hydrogen 1s orbital. The two types of bonds should be different in their energies. However, experiments show that methane has a regular tetrahedral structure. The 4 bonds in the methane have identical bond length and energy. The angles between all bonds are equal. In order to explain the bondings in multi-atomic molecules with a central atom, the orbital hybridization theory was developed. The orbital hybridization is the combination of atomic orbitals of an atom into new hybrid orbitals in order to form chemical bonds with orbitals of other atoms, which may also be hybrid orbitals. In general chemistry, we only consider the hybridization of s and p orbitals. The simplest orbital hybridization is the combination of the s orbital and one of the p orbitals. It is called sp hybridization. Here, I use the combination of 2s orbital and 2pz orbital as an example. There are 2 ways of linear combinations. The coefficients of the s orbital and p orbital are calculated by group theory, which is beyond the scope of general chemistry. You don't need to remember the coefficients, but you need to remember the shape of the sp hybridized orbitals. Both sp hybridized orbitals are cylindrically symmetric, with their positive lobes point in opposite directions. The shapes of the sp hybridized orbitals can be illustrated together by a schematic representation. Their symmetric axes are in a straight line. Each sp hybridized orbital can form a sigma bond with another atom. All 3 atoms are in a line. The 2s orbital has lower energy than the 2p orbitals. Being the combinations of s and p orbitals, the sp hybridized orbitals have energy between them. Here, we use carbon atom as an example. The electron configuration in its valence shell is shown on the left. The electron configuration after sp hybridization is shown on the right. There is a promotion of electrons from low-energy sp hybridized orbitals to high-energy 2p orbitals, because of the small energy difference between them. Thus, all the orbitals in the valence shell are half-filled, and can form bonds with other atoms. The sp2 hybridization is the combination of the s orbital and 2p orbitals. Here, I use the hybridization of 2s, 2px and 2py orbitals as an example. Again, you have to remember the shapes and electronic configurations of the sp2 hybridized orbitals. The hybridized orbitals have identical energy. They are all cylindrical symmetric. Their symmetric axes are in a plane and have 120-degree angle between each other. The sp2 hybridized orbitals can form 3 sigma bonds with other 3 atoms. They are at the vertexes of an equilateral triangle. Finally, the sp3 hybridization. This time, all the p orbitals are used. The hybridized orbitals have identical energy. They are all cylindrical symmetric and have 109.5-degree angle between each other. They can form 4 sigma bonds with other atoms. They are at the vertexes of a regular tetrahedron. The carbon atom in methane is sp3 hybridized. That is why it has a regular tetrahedral structure. Then, we use hydrocarbons with 2 carbon atoms as examples. In ethane, the carbon atoms are sp3 hybridized. The bonding between the carbon atoms is a sigma bond. It is by the overlap of the 2 sp3 hybridized orbitals, 1 per carbon atom. This carbon-carbon bonding is a single bond. In ethylene, there is a sigma bond by the overlap of the 2 sp2 hybridized orbitals. There is also a pi bond by the overlap of 2 2pz orbitals. Thus, this carbon-carbon bonding is a double bond. Since the sp2 hybridized orbitals are in a plane, and the two 2pz orbitals are parallel to each other, all the atoms in ethylene are in the same plane. In acetylene, there is a sigma bond by the overlap of two sp hybridized orbitals. There are also two pi bonds by the overlaps of the two 2px orbitals and two 2py orbitals. Thus, the carbon-carbon bonding in acetylene is a triple bond. Since the sp hybridized orbitals are in a straight line, all the atoms in acetylene are in a straight line. Not all the valence shell orbitals, including the hybridized ones, form bonding or antibonding orbitals. The valence shell orbitals which are neither bonding nor antibonding are non-bonding orbitals. The electron pair in a non-bonding orbital is a lone pair. Here, we use hydrogen fluoride as an example. The hydrogen 1s orbital and the fluorine 2p orbital form a bonding orbital and an antibonding orbital. Two electrons filled the bonding orbital to form a sigma bond. The fluorine 2s orbital is non-bonding because its energy is too low to interact with hydrogen 1s orbitals. The fluorine 2px and 2py orbitals are also non-bonding as they have long symmetry to interact with hydrogen 1s orbital. Thus, there are three non-bonding orbitals and three lone pairs in hydrogen fluoride molecule.